if you've been introduced to limits only non-rigorously, so for example, in a high school course, you haven't been given the definition of limit and you were told to just accept properties of limits without proof. We need the definition to prove these things. So in the last video, I talked about the formal definition of limit, and now I want to use it to show some of the basic properties. So let's show a few of them. So one, for any constant c, the limit as x goes to a of c is just c. 2, let's show that the limit as x goes to a of x equals a. 3, we're going to prove a additivity property. So if the limit as x goes to a of f of x is capital F, and the limit of g is capital G, then the limit of the sum, so as x goes to a of f of x plus g of x, is the sum of the limits. So capital F plus capital G. And 4, we'll do a multiplicativity, property, or the product rule for limits. It says that if the limits of f and g exist, and they're capital F and capital G respectively, then the limit of the product, so f times g, is the product of the limits. So capital F times capital G. Okay, so let's recall the definition of limit. Limit as x goes to a of f of x equals L means that for all epsilon greater than 0, there's a delta greater than 0, such that whenever x minus a in absolute value is less than delta, we get f of x minus L is less than epsilon in absolute value. So check out my last video if you want to see how this definition comes about and how to build it up from scratch. But let's use it now to prove some of these properties. So property 1, if c is a constant, then limit as x goes to a of c is just c. Proof, let epsilon be greater than 0, be arbitrary. And let's just pick delta to be 1. This is a completely arbitrary choice. You could take delta to be 87 because we won't actually need it for this one. Then if x minus a is less than delta in absolute value, then our f of x minus c, well, f is just c, so that's c minus c, which is 0, and that's less than epsilon because we picked epsilon to be larger than 0. So notice that we didn't actually need this condition on x. The delta and x don't matter for this proof. So that was a pretty simple argument, but let's do another fairly simple argument. Let's prove property 2, that the limit as x goes to a of x equals a. Proof, let epsilon be greater than 0. And this time we're going to take delta to equal epsilon. If x minus a in absolute value is less than delta, then our f of x minus our L, our f of x is just x, and our L is just a, so that's just equal to x minus a, and that's less than delta, which is equal to epsilon. So the proof just kind of did itself by choosing delta to be clever here. Okay, so now let's do a slightly more abstract property with proving the additivity. So now we're going to have to assume that certain limits exist to prove that another limit exists. So if the limit as x goes to a of f of x equals f, capital F, and the limit of g is capital G, then the limit of the sum f plus g is capital F plus capital G. And we could write that similarly as that's equal to the limit of little f plus the limit of little g. So you can interpret that as, okay, you can distribute the limit over the sum when they exist. The existence is an important part here. Okay, how do we do this? Proof, let epsilon be greater than 0. Then, since the limit of f is capital F, we can find delta 1 greater than 0, such that whenever x minus a in absolute value is less than delta 1, that implies that f minus capital F is less than epsilon over 2 in absolute value. Similarly, we can find a delta 2 greater than 0 such that, again, whenever x minus a in absolute value is less than delta 2, that implies that g of x minus g in absolute value is less than epsilon over 2. So this epsilon over 2, why am I picking that? You'll see in just a second. Now we're going to take our delta to be the minimum of these two deltas that we found. So the minimum of delta 1 and delta 2, so that delta is less than or equal to both of them because it's the smaller one of the two. So that if x minus a in absolute value is less than delta, then that means it's less than delta 1 and less than delta 2. So we can use both of our properties. Then the absolute value of the sum f plus g minus capital F plus capital G, I can rearrange them to get f minus capital F and g minus capital G. And I can use my triangle inequality here to get that this is less than or equal to the absolute value of f minus capital F plus g minus capital G. But each of these are less than epsilon over 2, which gives me a total of epsilon. So that first inequality came from the triangle inequality. Second one came from the fact that x minus a is less than both delta 1 and delta 2. And that gives us our argument. So it's a little bit abstract, and we had to assume the definition of limit for f and g individually to get this combined limit. So let's see a simple example of a limit to kind of combine what we've done so far. So let's show that the limit as x goes to 2 of x plus 5 equals 7. Proof. Since the limit as x goes to 2 of x equals 2, so that was by property 2, and the limit as x goes to 2 of 5 equals 5, and that again was by property 1. That means that we can use our sum rule that we just proved, so by property 3. That means that the limit as x goes to 2 of x plus 5 is the limit as x goes to 2 of x plus the limit as x goes to 2 of 5, which is just 2 plus 5, which is 7. So that avoids us having to do an epsilon delta argument. But one thing I'd invite you to ponder is, why do we need to check these limits exist? Can you come up with two functions whose limits do not exist, yet their sum has a limit? Okay, so this process seems cumbersome for now, but as we increase our results, our power will continue to grow and limits will get easy to evaluate. At least much easier than using the epsilon delta formalism all the time. Okay, so now we're going to look towards the product rule, or the multiplicativity of our limits. And just to remind you, the statement that says that if the limit of f is capital F and the limit of g is capital G, then the limit of their product, so f times g, is capital F times capital G. And again, we can write that instead as the limit of little f times the limit of little g. And we can interpret that as something like the limit can be distributed over the factors or into the factors of that product, again, when it exists. Okay, so this proof is going to be a bit more involved, but we can start by strategizing a little bit. So what do we want to show? Ultimately, we need to get this quantity f times g minus capital F times capital G to be small. We need to get that small. And we can use the fact that f times capital F and f minus capital F and g minus capital G can be made small using the fact that those limits exist. But it's not obvious how we do those here, because we can't do any kind of factoring that we see in that absolute value above. So the question is, how can we force those differences to appear in that absolute value that we see. So pause for a second if you like, but there's a trick. And that trick is to add 0. Of course, not just adding 0, but adding 0 in a clever way. So absolute value of f times g minus capital F times capital G is just f times g minus capital F times g of x plus capital F times g of x minus capital F times capital G. So notice that these two middle terms here add to 0. So I haven't changed the value. But the point now is that I can combine the first two terms and factor out a g of x. And the last two terms, I can factor out a capital F. And now my differences appear just like how I want them. So I can use my triangle inequality to get the differences that I like times g of x for f minus capital F, and capital F in absolute value times g minus capital G. So if we can control capital F and absolute value of g of x, then we're good. Capital F doesn't need to be controlled, it's a constant. But absolute value of g of x, we just need to make sure that doesn't blow up. Okay, so how do we do this? We're going to use the reverse triangle inequality. So lots of triangle inequalities in these arguments to say that the absolute value of g of x minus the absolute value of capital G is less than or equal to the absolute value of g minus capital G. So that's the reverse triangle inequality. So if that right-hand side is less than 1, say, we don't have to pick 1, but just for sake, then I can use the left-hand side to remove the absolute values and get that absolute value of g minus the absolute value of capital G is between 1 and negative 1. So again, that's just by combining those two inequalities and removing the absolute values. So that means that absolute value of g of x is less than 1 plus the absolute value of capital G. So that means we've controlled that quantity. It's less than some constant, so it won't blow up on us. This should work. Proof. Let's let epsilon be greater than 0. This is going to be a bit involved, but we can take it in stride here. So choose delta 1 greater than 0 so that if x minus a in absolute value is less than delta 1, then f of x minus f in absolute value is less than epsilon over 2 times 1 plus the absolute value of capital G. So why did I pick that? That seems strange, but you'll see why it cancels out beautifully in the end. Similarly, we want to pick a delta 2 greater than 0 so that if x minus a is less than delta 2, then we get a condition on the g's. So absolute value of g of x minus capital G is less than the minimum of 1 and epsilon over 2 times 1 plus the absolute value of capital F. Okay, so that 1 appears to get the inequality that we saw above, and adding the 1 in this denominator here just avoids the situation where capital F is equal to 0. We don't want to be dividing by 0. Okay, so then if we take delta again to be the minimum of delta 1 and delta 2, and x minus a is less than delta, then of course it's less than delta 1 and delta 2 again, just like we saw in the sum rule. So then we can look at our functions. So f times g minus capital F times capital G in absolute value. We can do this trick again of subtracting f times g of x plus f times g of x, and factoring and using our triangle inequality to get that this is f minus capital F times g of x plus g of x minus g times capital F. That's by our triangle inequality there. But that's going to be less than f minus capital F times 1 plus capital G in absolute value, plus g of x minus g in absolute value times 1 plus capital F. So that left part comes from the fact that g of x is less than 1 plus g, as we saw above, because g of x minus g is less than 1. And I'm just adding a 1 to that capital F. Okay, but now these differences cancel off nicely. So we see that f minus f is less than epsilon over 2 times that factor that is multiplying. So those cancel, and then g minus g is epsilon over 2 times 1 minus f, or sorry, 1 plus f, and those cancel off beautifully. So we're just left with two instances of epsilon over 2, which add, of course, to epsilon. And that's a completed proof. So that was quite involved, and it uses a trick that you get comfortable with when you deal with product limit arguments like this. And it's not at all intuitive or obvious for someone who hasn't seen it before. But at least we've checked with the epsilon delta formalism that it works now. So we can use the product rule the way that we like. Okay, let's take a bit of a breather and see the power of this. So let's do another limit example. Let's show that the limit as x goes to 2 of 2x squared plus 1 is 9. So doing an epsilon delta argument for this can be a little bit tricky, dealing with the x squared, but our properties that we've been proving so far make this much easier. So to do this, note that the limit as x goes to 2 of x equals 2, limit as x goes to 2 of 2 equals 2, limit as x goes to 2 of 1 equals 1 by properties 1 and 2. Now we can use our sum and product rules. So the limit as x goes to 2 of 2x squared plus 1 is the limit as x goes to 2 of 2x squared plus the limit as x goes to 2 of 1. That's our sum rule. And that's equal to the limit as x goes to 2 of 2 times the limit of x times the limit of x, because 2x squared is just 2 times x times x. And we have a plus 1. So that first equality came from our sum rule. Second one came from our product rule. And then we just evaluate the limits. That's just 2 times 2 times 2 plus 1, which is 8 plus 1, which is 9. So we made relatively short work of that limit by using our properties. Okay, so I'll end it here, but try for yourself a couple arguments. So give an epsilon delta argument to show that the scaling rule also applies. What do I mean by that? If c is a constant and the limit as x goes to a of f of x equals L, then the limit of the scaled f should be the scaled limit. So CF equals CL. And as a challenge, you can show that the quotient rule for limits is also true. So what do I mean by that? If the limit as x goes to a of f of x equals L, and the limit as x goes to a of g of x equals h, and it's non-zero, then the limit of their quotients is the quotient of their limits. So note that this is going to be quite a tricky argument and quite involved like our product rule. And there's one last thing to think about. Can you see why the properties that we've proved so far imply that any polynomial has this substitution property? Why we can evaluate the limit of any polynomial very nicely.